All right, good morning, everyone. Uh, Today, I'm going to wrap up chapter 4. We'll look at the last two equations for the step response for RL and RC, and then look at 3 examples, and that would be it for chapter 4. Homework for chapter 4 is due Sunday night, and quiz on Monday will be based on chapter 3. Okay, since we didn't have quiz last week, I want to test chapter 3. And you will see in the examples for chapter 4, since the equation is pretty standard for all 4 circuits, once you are done with the setup of the problem, you simply plug in the values into the equation. So the major portion of the analysis for chapter 4 problems comes from chapters 1 and 2, not from chapter 4 itself. Okay, and you will see that when we finish the 3 examples. All right, so let's get to our slides. And this is where we stopped: natural response, the analysis procedure. And it's going to the step response for an RL circuit. Okay, we have an inductor. We are told, again, from the circuit diagram, we are told that the switch closes at time t equal to 0, meaning it was open before the time equals 0. All that we can infer from here is that inductor is completely discharged. Okay. Now, whether it's charged or not discharged, we will take that into account in our equation. So when the switch closes, the inductor has a pathway to the voltage source. Vs is connected to the inductor L through the resistor R. And so current starts flowing. And the current that flows is labeled as I. Because it is a series circuit, the current I is the same for all 3 components. Okay. Initial energy of the inductor depends on, initial conditions of the circuit depends on the initial energy of the inductor. Now, in this case, we are assuming that the inductor did not have any charge. But again, in the equation, we will take it into account. Okay. So similar to the natural response derivation, we will apply KVL and we obtain a first order differential equation. The only difference between this and the natural response equation is that the sum of the voltages is no longer equal to 0, right? The final value is no longer equal to 0. It is equal to the source Vs. And so we have an extra quantity in our equation. And so when we solve this differential equation, we obtain an extra quantity in there. Natural response, remember, was V0 or V final into e raised to minus t over tau. We know the final value for a natural response is always going to be 0, right? It's discharging. Natural response means there is no external source, so it is discharging completely to 0. In this case, we have an extra quantity from Vs, and so that is the final value of that quantity. And in this case, it's IF. Okay, IF, final value, because that is what the inductor will reach, final level. And in most cases, IF final value will always be equal to the source. Source value. Okay. In this class, 201, non-EE majors, we do not do multi-step problems. In EE major, EE major classes, we would do multi-step problems where the inductor or capacitor would start charging to a certain level, then it starts discharging, but it would not discharge all the way to 0. So then it would start charging again, discharge, charge, discharge, and keep going on in multiple cycles. And so when we do multi-step problems, again, we break it up into each individual piece, and there will always be some initial energy stored in those components. Okay, but I don't do those for 201. Okay. In this class, the examples that you look at will always have a final value that is equal to the source value. And if it's discharging, then the final value will always be equal to 0. All right. So IF plus I0 minus IF into e raised to minus t over tau. This portion, of course, always remains the same for all 4 circuits. There's always an exponential form. So exponent is always included. The tau is a constant. It remains the same for a RL circuit for charging as well as discharging. Always be L over R, whether it's discharging or whether it is charging. And again, can have those on your equation sheet. You do not have to memorize it. But after you solve a few problems, it kind of becomes ingrained. Okay. Tau, time constant for a RL circuit, is always L over R. And then the reason I chose the voltage source is though I can show you that the current can simply be derived by using Ohm's law, right? The final value of the inductor current can be derived from Ohm's law. Initial value would be 0. IF would depend on the source. If a current source was given, we would simply take the current source value directly. But if it's a voltage source, apply Ohm's law and just, calculate the current from there. Make sense? Right? Okay. Then the same thing for a RC circuit. You have a capacitor. Capacitor is connected to a source. It starts charging when the switch is closed. Once it starts charging, current will flow through the capacitor. At some point, it will reach full charge. And when it reaches full charge, capacitor becomes open circuit. Current stops flowing through the capacitor. We apply KCL and we obtain a first order differential equation similar to natural response. Instead of 0, we now have the value as equal to the source current IS. Okay, but the form remains similar to the natural response circuit. Once you solve that differential equation, you obtain a solution that is exactly the same as the one we saw previously for RL circuits. Okay, so the for the inductor or for the capacitor, voltage is the same. Initial voltage in this case, actually, let me not write it down. Initial voltage for a capacitor in this example could be anything, but for most cases, it's always 0, completely discharged. Final value VF is again given from Ohm's law. So it depends on the source and the total equivalent resistance that is present in the circuit. Time constant tau is also the same. It's R times C, RC, and it's same for charging and discharging. R times C. Okay, no difference whatsoever. Now, if you look at the 4 circuits, all the equations have a very similar structure. Okay, so based on all 4 circuits, we can come up with a general equation that can be applied to all of them. Okay, and the steps also will be the same for all of them. And they will be summarized in a couple of slides. Actually, you know what? Right now. So general solution can be written as x of t is xf plus x0 minus xf into e raised to minus t over tau, where x, the variable, can represent both voltage as well as current. Okay, x can represent current. It can also represent voltage. So X can represent current and represent voltage. So the first step in determining a solution, whether it's for charging or for discharging, is you redraw the circuit for time t less than 0, and then redraw it again for time t greater than 0. And I will do and show that for the next 3 examples. Okay. Once you find the equivalent circuit, because there'll be multiple resistors or capacitors or inductors in the circuit, you would reduce it down to one single resistance, find Req. So first step is to always redraw the circuit, find the equivalent values, identify the variable X. If it's an inductor, you're trying to find the inductor current IL. If it's a capacitor, you're trying to find the capacitor voltage VC. Okay. Determine the initial conditions, and you can do that from your circuit diagrams for t less than 0. Okay. So you redraw the circuit for t less than 0 and then t greater than 0. This would give you the initial values, and this should give you your final values. So t less than 0, again, initial conditions, because initial is when time t equals 0. This is the moment in time when you begin your analysis. So you have 2 circuit diagrams, and because of the switching, the circuit diagrams are different. So t less than 0 would give you initial conditions, and t greater than 0 would give you final conditions. So once you have those values, then you find time constant tau, which is again standard equations, and then directly plug in the values in this expression. And you would have your answer. And that's it. As easy as that. Okay. The equation might seem complicated, but it only has 3 quantities. And if it's discharging, you only have 2. Right? If it's discharging, you only have 2 quantities because XF, the final value, would be equal to 0. So if you're discharging, the expression would work because XF is equal to 0 for discharging circuits. So you automatically eliminate those 2, and your equation simply becomes x0 times e raised to minus t over tau, which is the exact same equation that we obtained for the first 2 natural response circuits. Okay. Make sense? And that's why this equation works for all 4 circuits, because we take into account the initial values as well as the final values. All right, let's take a 10-second pause. Think over that and let me know if you have any questions. Yes. Oh, sorry. No, it should be x of t. This was pointing out that once you plug in xf into that equation, xf goes to 0. X of t is x0 into e raised to minus t over tau, which is the natural response. Natural response. Remember, for a natural response circuit, we assume that the initial value is full charge. Full charge. And so when it goes to step response, those are flipped. Initial is 0, and then final value is full charge. So it's 0 and full charge. For natural response, it goes from full charge to 0. And for step response, it goes from 0 to full charge. So the values get flipped over. All right, questions? Are we ready to move to to the examples. Okay. Before that, couple of slides about the chart. So I have a universal time constant chart here. And it simply is if you plug in the value of t as equal to the time constant, whether it's 1 tau, 2 tau, 3, 4, 5, and 6 tau, the values remain the same. Sorry, not the values. The shape of that function remains the same. It's exponent, right? So it follows an exponential curve, whether it's charging or discharging. So this is for charging. And this is for discharging. Okay, charging and discharging. And it doesn't matter how small or big the inductor and the capacitor are. The curve will always look like this. The only thing that changes would be the actual value. Okay, the actual value would change, but the curve or the graph will always look like this. It's simply the product of E, right? Doesn't matter what that product is. So the shape will always remain the same. The values for the time constant, when you plug in as 1, 2, 3, 4, 5 times tau, are listed in this table. The first thing I'd like to point out is this value. It's e raised to minus 1, which is 0.3679. 0.367. E raised to minus 1 is 0.3679. So when it's discharging, it is telling you that it loses 63.21%. Okay, it's V0 times e raised to minus 1. It's a product of V0, so max value. So when it's discharging, it loses 63.21% within the first time constant. So more than half is lost within the first time constant. And conversely, when it's charging, it acquires more than 63.21, not more than, it acquires 63.21% of the max value. So more than half is acquired after the first time constant itself. Okay, that's what those values mean. That's the first thing. That makes sense, right? The second point I'd like to make is that it's a mathematical equation, and which is the point I made earlier also. It's a mathematical equation. So if you plug in a value for t, a really large value, like a million or billion, you would always obtain a value for the current or the voltage, mathematically speaking. But in real life, it's always gone to 0 or it's always gone to full charge, right? Either it's max charge after a few minutes, it's always fully charged, fully discharged after a few minutes. So when do we put an end to it? When it's beyond 99%, which is 5 time constants. Okay, so 5 time constants right here allows it to go more than 99% of the way. So if it's charging, it acquires more than 99%. If it's discharging, it loses more than 99%. And so after 5 time constants, we put an end to it by standard or generally accepted convention. Okay, and so we say after 5 time constants, it's either fully charged or fully discharged. Okay, and that's why it's just generally accepted convention in electrical engineering that after 5 time constants, the inductor or capacitor has either reached full charge or full discharge. Okay, make sense? All right, 10-second pause. Let me know if you have any questions about anything we have done so far. No questions? Shall we move on to the examples? Yep. All right. Okay. The switch in the circuit has been closed for a long time before it is opened at t equals 0. Find IL of t for t greater than or equal to 0. First, look at what it's asking. It's asking for an expression for the inductor current. So let's look at the circuit, find the inductor. Right here. It's asking to find an expression for IL, the inductor current, as a function of time after t is equal to 0. So t greater than or equal to 0. Okay, so we need to derive. So first thing is, I'm going to draw the circuit prior to time t less than 0. Okay, prior to time t less than 0. So what does that give me? Gives me a current source, resistor, the switch, which is closed, inductor, and then 3 resistors on the right. So if the switch was closed prior to t equals to 0, and again, the keywords here are a long time. Remember what I said about a long time. A long time simply indicates the system is at steady state. The inductor is at a steady state because enough time has elapsed in the past that the inductor has reached full charge. Okay. And when the inductor reaches full charge, it behaves as a, anyone? Behaves as a short circuit. So if inductor is a short circuit, I'm just drawing it with 2 nodes, but you can simply draw a single line. It's a short circuit, so all of the current is flowing through that inductor. Nothing else goes to the resistors. None of the 4 resistors have any current. All of it goes through the inductor. So my IL value, since it's a short, at 0 minus is 20 amps. Again, I'll emphasize the equation is straightforward. You will have the equation in your equation sheet, but you should know how to analyze the circuit and extract all the values. So every word in this problem statement has some meaning. Okay, a very long time simply means that the system is at steady state. The component has time to reach steady state. In this case, because it is connected to the source, steady state would indicate that the inductor has reached full charge and it's behaving like a short circuit. Yes. So again, that's a very good question. The current would be split, but we are not concerned with anything that occurred in the past. Meaning we are not being asked to analyze the circuit prior to time t equal to 0. So the question being asked is about whether the current is passing through the resistors or not. Indeed, yes. So when sometime in the past, when the source was first connected to the inductor, yes, the current would have passed through the resistors and the inductor was slowly acquiring the charge. But the key word here is, again, a long time. The long time could be a few seconds, could be a few hours, could be a few days. We have no idea, and we actually don't really care. The only thing we should conclude from a very long time is that the system is at steady state, meaning the inductor has had sufficient time to reach steady state. And if it's steady state, we don't really care about how many resistors were connected in the circuit or which path the current took. Because you're indeed correct. In the past, it would be that all of the resistors did take some current, but all of the current was finally, the inductor, it allowed the current sorry, it allowed the inductor to reach full charge. Once it reaches full charge, it behaves like a short circuit and all of the current flows through that inductor. That's it. Because we are asked to analyze for t greater than or equal to 0, not for t less than 0. Okay. So again, a very good question, but the importance of the answer is that a very long time indicates the system is at steady state. So we are not being asked to analyze prior to time t equal to 0. It's only after time t equal to 0. Does that answer your question? Okay. All right. So prior to time t less than 0, inductor behaves like a short circuit. All of the current goes to the inductor. So IL at 0 minus is 20 amps. Then the switch is flipped. Time t greater than or equal to 0. The circuit looks like this. I have an inductor. The rest of the circuit is disconnected, meaning the source and the 0.1 ohm resistor is no longer part of the circuit. It's disconnected, right? It's no longer part of the circuit. Now the inductor is, and keep in mind, the inductor current direction is given to us. So we have to keep track because it is already implied in the problem statement. Not implied, sorry. It's already given to us or stated in the problem statement, which is in the circuit diagram. The current direction IL is going down. Okay, so we stick with that. Now, we have 3 resistors. Which resistor is the inductor discharging from or through? Through which resistor is the inductor discharging? Any guesses? Are they all part of the circuit? Yes. Then logically, it's discharging through all 3 of them. All 3 of them. So this requires me to find Req as seen by the inductor L. Remember, I have to reduce it down to one single resistance. So I have to find Req as seen by the inductor. As seen by means that inductor is no longer part of the circuit. We analyze and find R equivalent between those terminals. We start at the farthest end, and I can write Req is 40 in parallel with 10 plus the 2 ohm resistor. So that gives me 400 divided by 50 plus 2. That comes out to be 10 ohms. My Req is 10 ohms. All of the stored inductor energy is released through all 3 resistors. And again, for EE major classes, we would find the voltage and current for all 3 resistors. Here, I'm only asking you to find the expression for the inductor current, for nothing else. Okay. So we are still in the setup problem. Again, majority of the problem is just the initial setup. Okay, the initial setup is the majority of the problem. We are trying to find the 3 values: the initial values, the final values, and the time constant tau. Now we have Req, so we can calculate tau. And tau would simply be L over Req. L is 2 Henry, Req is 10. So this comes out to be 0.2 seconds. 0.2 seconds. Current through an inductor cannot change instantaneously. So IL 0 plus would be the same as IL 0 minus, which would be equal to 20 amps. Right? And that's the point of drawing the circuit diagrams for t less than 0 and t greater than 0. Because IL 0 plus would be the same as IL 0 minus. Let me write it down here again. Amps, and therefore the initial value of the current I0 would be 20 amps. And because it is a natural response problem, you can write final value is 0 amps. Nothing is stated in the problem about the final value. So we simply assume final value is 0 because it's a natural response problem. Final value is 0. I have all my values now. I can simply take the expression IL of t is equal to IF plus I0 minus IF times e raised to minus t over tau. Plug in the values for everything. I get 0 plus 20 minus 0 into e raised to minus t over 0.2. And then reduce, and I obtain the final expression. IL of t is 20 times e raised to minus 5t. And the units will remain amps, right? The quantity is current, I. Doesn't matter that it's a function of time, but the value still remains current, A, amperes. And this equation is valid for all values of t greater than or equal to 0. It's better. And you can see as an example, if you plug in t equal to 0, what do you get? E raised to 0. 1 times 20, 20 amps. So right at the moment the switch was flipped, value of current to the inductor is 20 amps. Right? So the equation is valid. If you plug in -1, then it's not going to be valid anymore. Yes. Sure. So the notation or the value. Okay. So 0 plus indicates time right. Well, plus indicates right after, and minus indicates right before. So 0 plus is the time right after 0 seconds, and 0 minus is time right before. And it does not have a finite value. It is simply expressing. It could be in microseconds or nanoseconds. It's simply used to determine the quantity of, to determine the value of that quantity right after the switch is flipped, which is I0, without which we would not be able to solve for the problem. So we simply use that concept to determine the value of the current or the quantity right after the switch is flipped. Because current through an inductor cannot change instantaneously, and voltage across a capacitor cannot change instantaneously. And so we use and extend that concept to determine the initial values in our problems. Okay. All right, think over this. Let me know if you have any questions. again, the majority of the solution is the setup. So you draw the circuit diagram for t less than 0 and t greater than 0, determine the initial values and the final values, and then find out tau, plug in all values into the standard expression, and that's it. Again, for this class, for 201, the final and the initial values are fixed. Okay, it has to do with the source. So it's charging up, it's charging from 0 to a max value. That max value would be equal to the source value. And if it's discharging, it's flipped. If it's discharging, max value is the source, which is already in the initial conditions. And then final value would be 0. So the initial and final values will be flipped for charging and discharging. Okay. All right, any questions before I move on to example 2? All right, example 2 is very similar, except this time we use a capacitor. Okay, same problem statement or similar problem statement. Switch has been in position X. It's a 2-position switch. So switch has been in position X for a very long time. Again, long time even indicates the system and the capacitor is at steady state, meaning the capacitor has had enough time to reach full charge. At time t equal to 0, the switch is flipped to position Y, thus disconnecting the source after time t equal to 0. And then capacitor simply begins to discharge. So let's draw the circuit diagram for t less than 0. For t less than 0, it's simply a source, resistor, and capacitor. And because a long time has elapsed, we would simply assume that VC is 100 volts. So value for VC at 0 minus is 100 volts. That's the initial setup. And then after the switch is flipped, t greater than 0, the source is disconnected. The fully charged capacitor is now connected to 3 resistors. Same thing as the previous example. You'd have to find Req. Req as seen by the capacitor. And so Req, in total Req in this case, is given by the 60 kilo ohm resistor in parallel with the 240 kilo ohm resistor, which is then in series with the 32 kilo ohm resistor. When you solve this, you obtain a value for Req as 80 kilo ohms. Okay, 80 kilo ohms. The fully charged capacitor is discharging through the 3 resistors. I can find the time constant simply by multiplying Req with capacitor C. So 80 kilo ohms times 0.5 microfarads. And so my tau is equal to 5/8 of 40 milliseconds. 40 milliseconds. For time t greater than 0, VC at 0 plus would be the same as VC at 0 minus. because the voltage across the capacitor cannot change instantaneously. And so I can write VC 0 plus equals VC 0 minus equals 100 volts. So initial value V0 is 100 volts. And final value VF would be equal to 0 volts. My time constant is 40 milliseconds, 40 milliseconds, right? So I would expect that it would reach full discharge after 5 time constants, which is 40 times 5, which is 200 milliseconds, right? 200 milliseconds. So about 0.2 seconds. Does that make sense? Right? So just to give you an idea of what kind of analysis would be expected in an E measure class, I would say after 0.1 milliseconds, the switch is flipped back to position X. What happens then? Now the capacitor is again connected to the source. It begins charging after 0.1 milliseconds. So it reached full charge. Then it started discharging. But before it could reach zero, it starts charging again. So in that case, you would have to take the initial value and then the final value again, and then just solve it. Not too complicated, but everything would be in that problem statement because the equation is still the same. The only thing is you'd have to find the final value and the initial value and then plug it into the equation. In this case, in this example, it is charging, it's discharging from the max value and is going all the way down to 0. Nothing is mentioned about interrupting, interrupting the discharge process. They simply open the switch. The switch is flipped from the source. It's flipped to the other side. Source is disconnected, and that's it. Don't overthink the problem. Okay, nothing is mentioned about what happens afterwards. We are simply told it goes to position Y, and that's it. So when it gets to position Y, it's discharging. Final value is 0. You have the tau value. Simply plug it into the equation, and you can write an expression for Vc of t as Vf plus V0 minus Vf. Into e raised to minus t over tau. And so Vc of t is 0 plus 100 minus 0 into e raised to minus t over 0.04. So expression for Vct is simply 100 into e raised to minus 25t. Expression is volts. Unit is volts, and this expression is valid for all time values greater than or equal to 0. Does that make sense? It's a natural response problem because there is no source connected. If there is no source connected, final value is always 0. So Vf is 0. Any questions before I move on to the final example? The steps make sense? This analysis that we are talking about here, t less than 0 and t greater than 0, that depends on the circuit. Okay, that will be different for every circuit. And what it will test you is your abilities from chapters 1 and 2. Okay, all the concepts that we learned in chapters 1 and 2, those are the ones that you would need. That's why I go slightly slow rate at the beginning in the in the first 2 chapters, because the first 2 chapters are very important. Okay, final example, example 3, simply states derive an expression for VC of t for time t greater than 0. Nothing else is given. It's simply a source and a resistor and a capacitor. So time t less than 0, the circuit actually looks like this. And then that's it. All of the current is flowing through itself. The current source is actually short-circuited. Okay. In real life, this is not something we would do, right? We would never take a source and just short-circuit the terminals. That's not something we would ever do. This is simply to show, again, this is simply to show that the capacitor is fully discharged to that resistor. So the resistor is R 2 kilo ohms, capacitor, whatever charge was present on that capacitor is fully discharged to that resistor itself, because it's not part of the circuit. So again, the logical conclusion that you should take from this is that the capacitor has no charge. So initial value for the capacitor is 0 volts. That's the only thing we want to infer from this. Okay. Capacitor is basically not part of the circuit at all because there is a short circuit. So VC at 0 minus is 0 volts. That's the only reason it's shown this way. Now the switch is flipped at time t equal to 0. So time t greater than or equal to 0, the switch is flipped and the capacitor begins charging through that resistor. Okay. 10 milliamps and 2 kilo ohms. Eventually, the capacitor will reach full charge, right? It's going to start charging the moment the switch is closed. I mean, the switch is open, and then eventually it will reach full charge. What is the value of that charge in terms of voltage? Remember, we just saw it a few slides ago. You have a current, you have a resistor. What is the voltage? No ideas? That's why I said chapter 1. V equals IR. So the final value of that capacitor voltage would be equal to the source current. IS is not stated explicitly, but I'll write it as IS. So 10 milliamps times 2 kilo ohms. And so final value of that voltage would be 20 volts. Just use given from Ohm's law. That's it. I can also do a source transformation where I would take the current source and transform it into voltage source, but effectively it's the exact same thing. Source transformation means I would still apply Ohm's law. That's the concept, right? V equals IR. So final value of the voltage is the source current times the resistor through which the capacitor is charging. If there were multiple resistors in the circuit, you would find Req as seen by the capacitor. Okay. So VF is 20 volts. Capacitor voltage cannot change instantaneously. So VC at 0 plus is equal to VC at 0 minus, which is 0 volts. Therefore, my initial voltage V0 is also 0 volts. Tau is simply the product of R and C. And so it's 2000 times 10 microfarads. Oh, I'm out of time. So if you need to leave, feel free to leave. I'm just going to finish writing this out. And then, you can look at the rest in the lecture video. So tau would be equal to 20 milliseconds. I have V0, I have Vf, and I have tau. I would plug it directly into the equation or the expression for Vc of t. So Vf plus V0 minus Vf into e raised to minus t over tau. And therefore, Vc of t is 20 plus 0 minus 20 into e raised to minus t over 20 milliseconds. Do not forget the units and the unit prefix. So Vc of t would simply be 20 minus 20 into e raised to minus 50t. This would be volts, valid for all values of t greater than or equal to 0. All right, we'll end class here today. Again, homework is due on Sunday night. Most of them are short answer questions based on concepts, and several students have already begun the homework, and some of them have even completed it. And then quiz on Monday based on chapter 3, not on chapter 4. As always, I will make sure that the announcement is posted by today evening. I will bid you all a good weekend, and I will see you all on Monday.